Chapter 15 deals with relational database design and algorithms and further dependencies. Here are the sections we'll be going over, 15.1 through 4, and then 15.5 and 6. Functional dependencies, inference rules, and equivalence and minimum cover. We discussed functional dependencies in the last chapters. To recollect, a set of attributes of X, X functionally determines a set of attributes Y if the value of X determines a unique value of Y. Our goal here is to determine the properties of functional dependencies and to find out the ways of manipulating them. X implies Y holds if every two tuples have the same value for X, they must have the same value for Y. For any two tuples T1 and T2, if any relational instance R sub R, if T1 sub X is equal to T2 of X, then T1 of Y is equal to T2 of Y. X implies Y and R specifies a constraint on all relational instances written as X implies Y can be denoted graphically as a relational schema as in figures in chapter 14 denoted by an arrow. Functional dependencies are derived from the real-world constraints of the attribute. Definition, inference rules for functional dependencies. X implies Y is inferred from or implied by a set of dependencies F specified in R if X implies Y holds in every legal relation state R of R. That is, every R satisfies all the dependencies in F, X implies Y also holds in R. Given a set of F functional dependencies F, we can infer additional functional dependencies that hold whenever FDs in F hold. Armstrong's inference rules are as follows. Inference rules for functional dependency, some additional inference rules that are useful. Decomposition, X implies YZ, then X implies Y and X implies Z. Union, if X implies Y, then X implies Z, then X implies YZ. And pseudo-transitivity, if X implies Y and WY implies Z, then XY or WX implies Z. The last three inference rules, as well as any other inference rules, can be deduced from IR 1, 2, and 3 through the completeness property. A closure of a set of functional dependencies F is the set of F plus for all FDs that can be inferred from F. A closure of a set of attributes X with respect to F is the set X plus for all attributes that are functionally determined by X. X plus can be calculated by repeatedly applying IR 1 through 3 using functional dependencies in F. Algorithm 15.1 is around determining X, the closure of X under F. The input is the set of F's in the functional dependency in the relational schema R, and a set of X, which is a subset of R, X plus X, and then repeat, and then so on. Example closure. For example, consider the following relational schema about classes held at university in a given academic year. The closure of attributes or sets of attributes of some example sets. Two sets FDs, F and G, are equivalent if for every F can be inferred from G and FG and G can be inferred from F. Hence, F and G are equivalent to F plus equals G plus. Definition covers F covers G, and every functional dependency in G can be inferred if F and G are equivalent, F and covers G, and so on. Finding minimal cover of functional dependencies. Just as we applied inference rules to expand on a set of FDs to arrive at F closure, it is possible to think in the opposite direction to see if we can shrink or reduce the set F to its minimal form so that the minimal set is still equivalent to the original set F. Definition: an attribute is a functional dependency is considered extraneous attribute if we can remove it without changing the closure of the set of dependencies formally given. F, the set of functional dependencies, and a functional dependency X implies A. If F attribute Y is extraneous, if X in X, if Y is a subset of F, of X and X logically implies. A set of FDs is minimal if it satisfies the following conditions. Every dependency in F has a single attribute for its RHS. We cannot remove any dependencies from F and have a set of dependencies that is equivalent to F. We cannot replace any dependencies X implies A in F with a dependency Y implies A's, where Y is a proper subset of X and still have a set of dependencies that is equivalent to F. Illustration of the algorithm 15.2 is as follows. We now have a set equivalent to the original E, say E prime. B implies A, D implies A, B implies D. No further reduction is possible in step 2 since all functional dependencies have a single attribute on the left-hand side. Minimal set of FDSs. Every set of FDSs has a equivalent minimal set. There can be several equivalent minimal sets. There is no simple algorithm for computing a minimal set of FDs that is equivalent to a set F of FDs. The process of algorithm 1512 is used until no further reduction is possible. To synthesize a set of relations, we assume that we start with a set of dependencies that is a minimal set. Designing a set of relations. The approach of relational synthesis bottom-up design assume that all possible functional dependencies are known, construct a minimal set of functional dependencies, then apply algorithms that construct a target set of third normal form or Boyce-Codd normal form relations. Additional criteria may be needed to ensure that the set of relations in a relational database are satisfactory. See algorithm 15.3. The goals is a lossless join property. It's a must. Algorithm 15.3 test for general losslessness. Dependency preservation property, observe as much as possible. Algorithm 15.5 decomposes the relation into Boyce-Codd normal form components by sacrificing the dependency preservation. Additional normal forms, fourth normal form based on multi-valued dependencies, and fifth normal form based on joined dependencies. Algorithm to determine the key of a relation. Algorithm 15.2a, finding a key K for R given a set of F's of functional dependencies is as follows. 15.2, properties of relational decomposition. 2.1, relational decomposition and insufficiency of normal forms. The universal relational schema, a relational schema R of A1 through N that includes all the attributes in the database. Universal relation assumption, every attribute name is unique. Decomposition, the process of decomposing the universal relational schema R into a set of relational schemas, D equals R sub 1 through N, that will become the relational database schema by using the functional dependencies. Attribute preservation condition, each attribute in R will appear in at least one relation schema R in the decomposition so that no attributes are lost. Properties of relational decomposition, third of 11. Another goal of decomposition is to have each individual relation R in the decomposition D be in B, C, and F or third normal form. Additional properties of decomposition are needed to prevent from generating spurious tuples. 2.1, dependency preservation property of a decomposition. Definition, given a set of dependencies F on R, the projection of F on R1 or Ri denotes by P sub RIF, where Ri is a subset of R, is the set of dependencies X in that implies Y in F closure such that the attributes in X union Y are contained in Ri. Hence, the projection of F in each relation schema R in the decomposition D is the set of functional F closure dependent upon the closure of F such that all their left and right-hand side attributes are in R sub I. Dependency preservation of a decomposition continued. Dependency preservation property, a decomposition D equals R sub 1 through M of R is dependency preserving with respect to F if the union of the projections of F on each R sub I in D is equivalent to F, that is, and so on. The claim 1, it is always possible to find a dependency preserving decomposition D with respect to F such that each relation Ri in D is in third normal form. This is a Boyce-Codd normal form dependency diagram. Figure 14.12 is the normalization of second normal form and third normal form in the second screen. Properties of relational decomposition, non-additive lossless join property of a decomposition. Definition, lossless join property, a decomposition D of R1 through M of R has lossless non-additive join property with respect to the set of dependencies F on R if for every relation state R of R that satisfies F, the following holds where star is the natural join of all of the relations in D. Note that the word loss and lossless refers to the loss of information, not the loss of tuples. In fact, the loss of information is better termed in addition of spurious information. Algorithm 15.3 test for the lossless join property. Repeat the following. This is a continuing on of that process. Figure 15.1 is the non-additive join test of n-ary decompositions. Testing binary decompositions of non-additive join, lossless join property, binary decomposition of relation into two relations. Property in NJB is the non-additive join test for binary decompositions, and so on. Successive non-additive join decomposition. Claim 2, preservation of non-additive in successful decompositions. If a decomposition D sub R1 through N M of R has the lossless non-additive join property with respect to a set of functional dependencies F on R, and if a decomposition Di of Q1 through K of Ri has the lossless non-additive join property with respect to the projection of F on R sub I, then the decomposition D2 is equal to R1 through M of R that has the non-additive join property with respect to F. Algorithm 15.4 is the relational synthesis of third normal form with dependency preservation and non-additive lossless join property. Algorithm 15.5, relational decomposition into BCNF with lossless non-additive join property. 15.4, problems with null values and dangling tuples. Problems with null values. When some tuples have null values for attributes, they will be used to join individual relations in the decompositions that may lead to incomplete results. For example, figure 15.2a, where two relations employee and department are shown, the last two employee tuples represent newly hired employees who have not yet been assigned to a department. Assume that this does not violate any integrity constraints. If we want to retrieve a list of employee name, department number, values for all employees, if we apply a natural join operation on employee and department, the two aforementioned tuples will not appear in the results. As in such cases, a left outer join may be needed. The results are shown in 15.2c. Continuing the discussion of problems with dangling tuples, consider the decomposition of employee into employee 1 and employee 2 as shown as figure 15.3a and b. Their natural join yields the original relation employee in figure 15.2a. We may use the alternative representation shown in 15.3c, where we do not include a tuple in employee 3 if the employee has not yet been assigned to a department, instead of including a tuple with a null for denom as in employee 2. If we use employee 3 instead of employee 2 and apply a natural join on employee 1 and 3, the tuples in Berger and such will not appear in the results. This is called dangling tuples in employee. Discussions of normalization algorithms, problems. The database designer must first specify all the relevant functional dependencies among the database attributes. These attributes are not deterministic in general. It is not always possible to find a decomposition into relational schemas that preserves dependencies and allows each relational schema in the decomposition to be in BCNF instead of third normal form as in algorithm 15.5. A multi-value dependency, MVD, X implies Y, specifies on a relationship R where X and Y are both subsets of R, specifies the following constraint of any relation state R of R. If two tuples T1 and T2 exist in R such that T1 sub X minus T2 sub X, then two tuples T3 and T4 should also exist in R. The following properties we use Z to denote um, and so on. Inference rules for functional multi-value dependencies are as follows. A relational schema R is in fourth normal form with respect to a set of dependencies F that includes functional dependencies and multi-value dependencies if for every non-trivial multi-value dependency, X implies Y, in F closure, X is a superkey of R. A definition of fifth normal form, a relational schema R is in fifth normal form or project join normal form, PJ and F, with respect to a set of F functional multi-valued and joined dependencies if for every non-trivial joined dependency, that is F implied by F, every R sub I is a superkey of R. Discovering joined dependencies in practical databases with hundreds of relations is next to impossible. Therefore, fifth normal form is rarely used in practice, if ever. Um, Inclusion dependency R.X is less than S.Y between two sets of attributes X of R relations schema R and Y of relation schema S, specifies the constraint that at any specific time when R is in a relational state R and S is in a relational state of S, we must have, and so on. Objective of inclusion dependencies to formalize two types of interrelational constraints which cannot be expressed using functional dependencies or multi-value dependencies. Referential integrity constraints, class, subclass relations, inclusion dependency inference rules, and so on. Algorithmic functions, as long as the unique value of Y is associated with every value of X, we can still consider that to be a functional dependency, that the functional dependency X implies Y exists. For example, consider the relations order line, order number, item number, quantity, unit price, extended price, and discount price. Each tuple represents an item of an order with a particular quantity and the price per unit for that item. In this relation, quantity unit price implies extended price by the formula. Hence, there is a unique value for extended price for every pair and thus conforms to the definition of functional dependency. Functional dependencies based upon algorithmic functions and procedures. There may be a procedure that takes into account the quantity discount, the type of item, and so on, and computes a discounted price for the total quantity ordered for that item. Therefore, we can say the following. Domain key, normal forms, definition. A relational schema is said to be in DKNF if all constraints and dependencies that should hold on the valid relation states can be enforced simply by enforcing the domain constraints and key constraints for the relation. The idea is to specify, theoretically at least, the ultimate normal form that takes into account all possible types of dependencies and constraints. For a relation in DKNF, it becomes very straightforward to enforce all database constraints by simply checking each attribute value in a tuple to see if the appropriate domain and that every key constraint is enforced. The practical utility of DKNF is limited. To recap, we talked about functional dependencies and revisited them. We talked about designing a set of relations by synthesis. We talked about properties of relational decomposition, algorithms for relational database schema design in third normal form and Boas-Codd normal form. Then we talked about multi-value dependencies in fourth normal form. Other dependencies in normal forms were also discussed. And with that, we've reached the end of this discussion. If you have any questions, feel free to reach out. That's what I'm here for. Otherwise, stay safe, and we'll speak again next week.